Good morning, dear students. Hope you have enjoyed a vacation at home. Hope you are staying at home safely. Don't come out as we are under a pandemic disease COVID-19. So here is our attempt to demonstrate the experiment which you might have forgotten because long gap has been given due to this unusual incidents. So here we are going to demonstrate your final year BSc experiments which you are going to get in your practical examination. So please go through this, and if you have any queries, feel free to ask in our group. The aim of the experiment is potentiometric titration, that is potentiometrically you have to determine the strength of ferrous ammonium sulfate using potassium dichromate solution. So here is all setup is made. So whenever you enter into the lab, you can find this instrument. It is potentiometer, dichromate solution which will be supplied to you in the reagent bottle, and ferrous ammonium sulfate solution which will be supplied to you in this small beaker. This is ferrous ammonium sulfate solution, and in that you can find a magnetic stirrer. So this is potassium dichromate solution. You have to take it in the microburette. So to start with the titration, this ferrous ammonium sulfate solution, first you should acidify with the half test tube of dilute sulfuric acid. So add half test tube of dilute sulfuric acid to this beaker. So then in this beaker you have to insert two electrodes. One is experimental electrode, other one is reference electrode, that is calomel electrode. This is calomel electrode and this is experimental electrode, that is platinum electrode. Connect these electrodes first to the instrument in the proper socket. So you can find the black terminal of this calomel is connected to this instrument, and the red terminal of this electrode is connected to the red socket. So connect these electrodes like this and dip it in the solution which you have taken in the beaker like this. Take care to see that the platinum and the calomel strip is dipped inside the solution. So this is the setup which you have to do. So in the instrument you can find these switches. So here you can see standard cell in and out. So now it is in, that is red light is showing in, that means it is 1.017. So in the beginning when the standard cell is in, it should read 1.018, and if it is not reading, just rotate this screw to make it 1.018. Now it is standardized. So this is the first setup you have to do to standardize this cell. This button should be in, that is red light should shown in that way. That is, after making standardization, put the standard cell out by pressing this button. So now you can read, this reading is a EMF. That is, you have dipped the cell in the solution which will show the EMF of this cell. So theoretical background of this cell is, that is reduction potential of the electrode is given by the expression E equal to E naught of Fe3 by Fe2 plus 0.05915 into log of Fe3 by Fe2 plus. This is the expression for the reduction potential of this platinum electrode which are going to dip in the solution, and that platinum is in contact with Fe3 plus and Fe2 plus ions as the reaction proceeds. So this is the reduction potential for that particular electrode. And when it is coupled with the calomel electrode, this is the calomel electrode. When it is coupled with that calomel electrode, platinum and calomel electrode, it forms a cell. So when that cell is formed, EMF of that cell is given by this expression. E of the cell would be equal to E experimental minus E calomel, which is already studied in your theory class. That is right hand side electrode minus left hand side electrode, like that. Here there is no such restriction is given. It is E experimental, that is platinum electrode, and E calomel, that is reference electrode. And E experimental means it is our platinum electrode, that is this expression. I have substituted here this expression, and minus E cal, this one. So in order to rearrange this expression minus E can, I have taken this other side, that is plus 0.05915 into log of Fe3 concentration by Fe2 plus concentration. This is all Nernst equation which I have discussed in the class very well. So all we are going to study the concentration of this Fe3 plus by Fe2 plus. How does it vary when the experiment is carried out? So EM of the cell is entirely dependent on the concentration of Fe3 to Fe2 plus ratio. And therefore, as you know very well, you have taken ferrous sulfate in the beaker and you are adding potassium dichromate from the burette. So potassium dichromate is an oxidizing agent which oxidizes ferrous ions into ferric ions, and therefore the ratio of the concentration of Fe3 plus ions to Fe2 plus ions changes as titration proceeds. And that's what we are recording in the potentiometer. And the potentiometer will give you, this digital display will show you the EMF of the cell, and that is recorded according to the tabulation. So now we have 10 ml of ferrous sulfate in this beaker, half test tube of dilute sulfuric acid, magnetic stirrer. So we will proceed with our titration. First, rough titration we are going to do, as you know, to find out the end point of the titration in an interval of 1 ml. So rough titration is carried out 1 centimeter cube time 1 centimeter cube interval. So first I will add 1 centimeter cube of dichromate from the burette. So added 1 centimeter cube, then bring it to the stirring position, lift the electrodes, stir, put on the stirrer button on, allow it to stir for 5 to 10 seconds, put off the stirrer button, stop, dip the electrode in the solution, see to it that platinum and calomel strips are dipped properly. So now we can see this record, that is the EMF. This value should be recorded against 1 ml of dichromate, that is first reading, that is 336, imagine. It is coming as 336. So we can record that here 336. Correspondingly, the next 1 centimeter cube interval, 1 centimeter cube you have to add from this dichromate to this. Again bring it to this position, stir it, 1 centimeter cube like this you have to add and record this rough value. So by looking at this rough value, you can see where there is a maximum difference, and that indicates the jump, or there is an end point at that particular volume. And therefore, by looking at this reading, you can see here 336, 397, 410 like this, and here 6 you got 0.451 and 7 you got 565. So this means from 6 to 7 there is a marginal jump, and therefore you can say that the end point of the titration is between 6 and 7, and this only gives you the rough idea where the end point is there with 1 centimeter cube interval, and that is not accurate. And for accuracy, that is for 0.1 cc ml, you have to do again repeated trial. That is, this is only for rough trial, and next again wash this beaker, pipette out again 10 ml, which will be given in 2 sets. That is, take the next beaker which consists of this, imagine it is consisting of 10 ml of ferrous sulfate, again add half test tube of sulfuric acid, again transfer this stirrer to the another beaker and wash these electrode and dip in the another beaker and fill this burette with again dichromate solution, repeat the titration, and that is fair reading. And in the fair reading, you have to systematically record the values like this. You have to start from 1 ml, 2 ml, 3 ml, and you know the end point is between 6 and 7, and therefore from 6 you have to add at 0.1 interval till 7, 0.1 cc, and then after that you can add again 1 cc interval 7, 8, 9. So record this reading properly, and this EMF record in this column, and the bigger value minus smaller value delta E, and 2 minus 1, this is delta V volume. It will be 1, 1, 1 here till here, and from here it becomes 0.1 volume difference, and suppose if it is 0.336 and next value if it is 0.397 and the difference here, this minus this will come here value. So it is 1, 6 and 0. This is the difference value 0.061. So this value like that, this value minus this value here, this value minus this value here, this value minus this value here, volume this minus this here, like that you will record, and this divided by this you will get delta E by delta V value. And once you get this value, you have to plot the graphs, that is delta E by delta V value against volume of dichromate. When you plot this, you will get this type of graphs, and you will get a peak. This peak is important. From the peak you draw a vertical line, and if cut this point, and here you have to record the volume. Suppose if it is 6.6 and this 6.6 is the end point of the titration. That's your experiment. First value you have to record, this is the end point of the titration, 6.6. And once you record 6.6, another graph you have to plot, that is EMF versus volume of dichromate. EMF of dichromate, EMF of the experiment against y-axis and volume of dichromate against x-axis, and you will get a graph like this. And when you get a graph like this, you know already the end point of the titration. Suppose if it is 6.6, that is the volume here, first volume, that is 6.6 would be 1 point, and that is not required for you, and you need only the volume at half neutralization point. That is half neutralization point of this means 6.6, half neutralization points, it would be around 3.3. So from 3.3 you have to draw a vertical line because it is a half neutralization point, and from that line, straight line towards EMF you draw. So this is the EMF at half neutralization point, and this EMF you have to record to calculate the redox potential, and redox potential would be equal to EMF of the cell at half neutralization point plus E of calomel. EMF of the cell at half neutralization point and calomel electrode, potential of the calomel electrode. And this E of the cell at half neutralization point you will get from the graph. This value of the substitute here, and E of the calomel is constant, that is 0.245, and that you substitute and get the redox potential. And this is the experiment for this potentiometric titration. And if you have any doubt, please feel free to ask. Thank you.